vector space and you have equipped with an inner product, and with respect to the induced norm, it gives you a metric and the vector space is complete. So it's a metric space. Metric comes from norm and the norm comes from inner product. So there are so many structures into it. You can think of it as just Cn, okay, n-dimensional complex Hilbert space. And operators are linear transformations between two Hilbert spaces, preserved structures, linear structures, which you can think of as matrices, okay? So this is a joint work with my first postdoc mentor, Bhattakrishna Das from IIT Bombay. And the problem that we proposed could not solve, only partially we solved. So the purpose of this talk is to just tell you what this problem is about. And okay, so take a compact set, a closed bounded set in the d-dimensional complex space. Please, you can, if you want, you can think of it as just the complex plane and a tuple of commuting operators. So it's a d tuple of commuting operators. If d is equal to 1, then this is just a single operator, meaning linear transformation. You can think of it as a matrix acting on a Hilbert space H. You say that K is a spectral set, okay, for T. If for every polynomial f in d variables, if d is equal to 1, it's one single variable polynomial. The norm of ft, so you plug in t in place of z, so if it's a polynomial, and you look at the norm, operator norm, and this is what that means. You're looking at the supremum of FTH, the norm of FTH, where H runs over the sphere. And that should be less or equal to supremum of F over K, the compact set. If that happens for every polynomial, then you say that it's a spectral set for T. You say it's a complete spectral set. If this happens, not only for scalar valued polynomials, but also for n by n matrix valued polynomials, okay, for every n greater or equal to 1. So, you know, the one easy way to think of a polynomial with matrix valued is it's a matrix with polynomial entries, and you know what? So f of f is equal to f of z equal to f of f sub ij equal to 1 to n, and so f of t is equal to f sub I z t. So you look at the operator norm of that, and that should be less or equal to the norm of f over the compact set. So from the definition, you see that a complete spectral set in particular is a spectral set because complete spectral set is asking more. You want that to happen for every n equal to 1, every n. And this is a operator algebraic way formulation of the problem. I mean, this is operator algebraic terminology, and this is an operator theoretic way of looking at it. Okay, so this happens equivalently, something happens. This I don't want to talk about today. I'm going to avoid that. This is operator theoretic way of looking at it. So the question is, so of course a complete spectral set is a spectral set. The question is the converse. When is the converse true? When is a spectral set a complete spectral set? That is indeed the holy grail in the spectral set theory, which is called the dilation problem. The dilation problem asks you when a spectral set is a complete spectral set. So you have a compact set. You are asking, is a spectral if you have an operator so K is a compact subset of the complex plane. T is an operator for which K is a spectral set. Is it necessary that K is a complete spectral set? So when is a spectral set a complete spectral set? Referred to as the dilation problem. This problem turns out to have a wide range. So it's yet not, there is no characterization of such compact sets known for which a definitive answer can be given. Okay, so but the planar case, that is the case when K is a subset of the complex plane, is better understood. Okay, so I'm going to walk you through the history of successes and failures. It turns out that the geometry of the compact set comes in. Okay, in fact, we use a lot of complex analysis. So when is a spectral set a complete spectral set? The answer is when K is disclosure. So disk is also Z in the C. So the modulus of Z is less or equal to 1. So it's just a unit disk. Or more generally, when K has a connected complement. So you look at the complement of K and you give me any 2 points, I should be able to connect those 2 points by a curve. So when this happens, and when whenever this K is a spectral set, it's a complete spectral set. When K is an annulus, so there's a big hole, you have a disk and you remove a tiny disk from it. When K is an annulus, this is it's a complete spectral set, but not when interior of K has 2 or more holes. So if you have a if you have a disk and if you remove 2 disjoint disks from it, then it is not going to be a complete spectral set. There is an example. And this is also, I have cited the work, the legends that who have done this, the stalwarts. When K is a bidisk, then also it's a spectral set. Whenever it's a spectral set, it's a complete spectral set, but not when K is the tridisk. So you see, you see what tridisk, this is tridisk, a Cartesian product of the disk 3 times. So you see when K is a disk, it's affirmative. When K is the bidisk, it's affirmative, but it fails for the tridisk onwards. So it has a rather mysterious history of successes and failures. Our interest lies in the case when K is an algebraic variety intersected with the closed bidisk. And so before I propose the problem, I want to walk you through why you might want to care about dilation theory. So it gives you a very different approach to, much easier approach, I would say, to the peak interpolation problem, which asks you, so you have been given Zj and Wj from the bidisk. So Zj are distinct, J equal to 1 to n, Wj may be equal. The problem asks you, when does there exist an analytic function such that it maps the to the final data Wj. So for an analytic function, you can think of it as a polynomial but of infinite degree. Okay, you can think of it as that, and with some sort of convergence going on there. So it gives you an easy, quick proof of that interpolation problem. It gives a different approach to still open problem, which is referred to as the invariant subspace problem. It doesn't help much, but nevertheless it gives you a different way of looking at the problem. So the problem asks you, does every Hilbert space operator have an invariant subspace? Very easy to formulate, but it's not yet known. It's not really, so it's solved in some cases, like if you have a Hilbert space of which is not separable, so it's a metric space, you know what separability means. So if it is not separable, then the answer is affirmative. Every operator has a Hilbert space, invariant subspace. If you have a Banach space, then it is negative. So if you remove the inner product structure, then it fails. The problem is still open when the Hilbert space is separable, okay? Unfortunately, but there are recent 2 papers posted on arXiv this year claiming to have solved this problem. It's only a matter of time to know if it is correct or not. 2 distinct papers, by the way. So dilation theory also gives you an operator theoretic representation formula for bounded analytic functions. I don't want to go into that. So it gives you a operator theoretic representation. You have a bounded analytic function, you can represent it. You can represent it in terms of operators, which is very nice, very helpful. And it brings down the study of abstract operators acting on abstract Hilbert spaces to the study of analytic functions. The theory of analytic functions is very rich. So, it helps to think of operators as functions in some way. And a concrete example to give you that demonstrates this statement is 2 operators are unitarily equivalent if and only if some functions, analytic functions corresponding to them coincide. Okay, so there is a notion of coincidence here. And I told you that I want to investigate the dilation problem when K is an algebraic variety. So this is what the variety that I was talking about. A distinguished variety is an affine variety. So xi is a polynomial in 2 variables that satisfies this. It should intersect the open bidisk, okay, and it should exit the domain through the torus. Okay, it should not intersect the other part of the boundary. For example, you can take z1 minus z2, the simplest one you can think of, or z1 square minus z2q. Okay, and for a non-example, you can think of, so you can perturb the first example by by multiplying something that is not allowed. So you can, if, for example, you say, well, the open bidisk, but it doesn't satisfy the boundary condition. Because, for example, 1, 0 is in the 0 set, which is not in the torus. Neither is it in the open bidisk. Well, these varieties are important. So the real importance of these varieties come up in work of Agler and McCarthy in 2000. They prove this. Okay, so very simple result. If you have T1, T2, a commuting contractive matrices. So by contractive, I mean the operator norm should be less or equal to 1. It contracts the ball. Okay, commuting contractive matrices with all their eigenvalues in the disk. So they are not allowed to have eigenvalues on the circle. You can still find a way, but in their theorem, hypothesis was written in this way. Then if you have such a pair of commuting matrices, then there exists a distinguished variety. You have seen what that means. Certain special variety such that 0 set of eta intersected with the closed bidisk is a complete spectral set, meaning this inequality is happening for every n by n matrix valued polynomial. Now, why is this important? This is very nice because such a thing was known due to Ando when you took the supremum over the closed bidisk. Okay, please remember this is a very thin subset of the bidisk. Okay, so this is a major sharpening of this inequality. You will see that much of the main object of our work is to know whether or not the matrices are of any special kind here. Okay, we want to know if we could have this inequality happening over a distinguished variety, not over the whole bidisk, for pair of commuting operators other than matrices. Okay, we want to drop the finite dimensionality, and you will see that it could not get away from finite dimension. You will see in some way we did extend, but had to say that we could not solve it in the real infinite dimensional case. You will see. First question is, are distinguished varieties complete spectral set? Answer is no, and this is there are examples. If you take this example, we saw that this is a distinguished variety. Then there is a commuting contractive matrix pair which has this as a spectral set, but not a spectral set. That's what it means by it fails. That's what it means by certain set is not complete spectral set. It is a spectral set for some pair, but it's not a complete spectral set. And please note that the example is found in the finite dimension case. We are asking a revised question. We're revising the question. Okay, so this pair does not have this guy as a spectral set. But we will be happy, as far as our goal is concerned, we will be happy if this guy had a different variety as a complete spectral set. So the question is, does there not exist another distinguished variety, 0 set of eta, maybe not this, such that 0 set of eta intersected with the closed bidisk is a complete spectral set? And you know what that means here. Turns out that this is going to be a necessary condition. Okay, right. So so this is a necessary condition. The main result that we have proved is this. Okay, the extent that we could solve the problem to. So if you have a commuting contractive pair of operators, not just matrices, but for operators, it's allowed to act on infinite dimensions, such that it is annihilated by something, by a polynomial defining a distinguished variety. So, and we saw in the previous slide that this is a necessary condition. You could not get away with it. So let it be there. And something that you are not proud of is this. You took T1, we take T1 and T2 such that you look at this operator. So this is an adjoint. So you have a matrix Aij, and the adjoint is Aj bar. So it's the adjoint of the operator T2, operators Tj. You look at that operator, look at its range, which is a subspace, look at its dimension. If that is finite dimensional, so you see, that's what I meant by we could not get away with finite dimensionality. We need some finite dimensional condition. If that happens, then there exists an eta defining a distinguished variety such that this happens. Okay, so we have been able to extend the result to infinite dimension case, but not really. I mean, we did, but this is a very stringent condition, I would say. Okay. And this is, like I said, this is an ongoing work. And we hope to, there are evidence, there are reasons why we believe that we would be able to drop this. As you would agree that this extends earlier result of Aguilar and McCarthy, and this is not the only work that which puts an effort to extend this result of Aguilar and McCarthy to infinite dimension. My collaborator and his collaborator Das and Sarkar, they have tried this, and they had the same inequality, but they had even stronger condition there. Okay, that's it. Yeah, this is the paper where I proposed the problem, and the referee calls it a constrained anodilation problem, which I like calling the problem. And this is the work that we are preparing now. Yeah, thank you.
I think this belongs to the domain of algebraic geometry.
Yes, it does, and we know very less about that. Yeah.
Oh, you have talked of matrices on the one hand and analytic function on the other hand.
Yeah.
And you are talking of Hilbert spaces.
Okay.
So Hilbert spaces, one is on a function space, and the other one is algebraic entity. So I just do not get how do you bring these two together on the one hand, and secondly, can your matrices be infinite dimensional?
So when you say can the matrices be infinite dimension, what exactly do you mean? Absolutely. So when you talk about operators, it's allowed to be. So you can think of an operator as a, infinite by infinite size matrix. Okay. You can think of matrices operators as matrices of infinite size. First question is, how do you relate to operators and varieties? This is because, this is again by Aguilar and McCarthy. They noticed that if you have so this is the operator theoretic side of it, okay, which I avoided for this talk. If you have a T1 and T2, then you can dilate it to V1, V2. V1, V2 are nice. V1, V2 are commuting isometries, and it turns out that this thing happens if and only if you are able to dilate this T1 and T2, whatever that means. I didn't worry about, I didn't define that. If and only if you are able to T1 and T2 to V1 and V2, which lives in such a thing, meaning its joint spectrum. Okay, the joint spectrum of V1, V2 is an algebraic variety. Okay, so indeed that is the reason why we need this finite dimensionality. We need a lived. We need to dilate T1, T2 to V1, V2, which lives, meaning the joint spectrum should be a distinguished variety. That's why we're crucially using the finite dimensionality assumption.